Hello, this is the introductory video for the linear algebra and statistical methods portion of the course. We'll use this lecture to introduce linear algebra and make some definitions, and primarily what we're going to talk about today are matrices and vectors. So linear algebra is a fairly extensive subject. It covers vectors and matrices, determinants, systems of linear equations, vector spaces, linear transformations, eigenvalue problems, and lots of other topics. And in using modern statistical analysis and things like regression, it's important to have a good foundation in linear algebra. This lecture probably will be a review of a lot of topics that you've already covered. Just bear with me. If you prefer to just look through the slides and make sure you have the background, then probably no need to watch the lecture video. So the definition of a matrix is it's a rectangular array of numbers or functions that is usually enclosed in brackets. Here are some examples of matrices. I want to refer you to the one with the A's with the subscripts. So these are referred to as indices. They refer to row and columns. The first subscript refers to the row and the second subscript refers to the column. So for example, ece5371 is a specific reference to the second row, third column element in the matrix. This A matrix is an example of a square matrix. It has the same number of rows and columns. But matrices don't have to be square, so here's an example of a numerical matrix. 2 rows, 3 columns. And here's an example of a matrix that has functions. So that's certainly possible. This matrix is square because it has the same number of rows and columns. This is referred to as a row matrix or a row vector because it's a matrix that consists of a single row. This is referred to as a column matrix or column vector because it has a single column. So that's some of the notation that you'll see when discussing matrices. We'll go over some additional definitions. So here's a matrix. Noted that the notation is a bold capital letter in this textbook that we're using this semester. And that can also be written as square brackets with the lowercase a and the subscripts j and k, where j and k are indices that refer to row and column. So in this case, j, referring to the row, would vary from 1 to m, and k, referring to the column, would vary from 1 to n. This would be referred to as an m by n matrix because it has m rows and n columns. Now, if m and n are equal, we would call it an n by n square matrix, and the diagonal that has equal indices would be referred to as the main diagonal of the square matrix A, but that's only in the case if A were square. A vector, as we said before, is a matrix that has either only one row or one column. Its entries are called the components of the vector. We can denote vectors by lowercase boldface in this particular textbook, or by the generalized component in brackets, and in that case we'd only have one index, aj, because we only have one dimension. We say two matrices are equal if and only if all of their elements are equal and they have the same size. So A is equal to B if A11 is B11, A12 is B12, and so on. If matrices are not equal, we say they're different. When adding matrices, the sum of two matrices A and B, first of all, you have to have matrices of the same size if you're going to find their sum. And then you add element by element. So the j-kth element of A is added to the b-kth element of B, and then your corresponding result is a single matrix that is the sum A plus B. Scalar multiplication is the product of any m by n matrix A with any scalar C and that's written as C times A. And basically in that case, then each element within A is multiplied by the scalar C. So some simple rules, very simple, very similar to algebraic rules for matrix addition and scalar multiplication, just summarized here, very similar to the basic rules of algebra, the distributive property. Here in part C of the first set of rules, this 0 denotes the zero matrix. It takes on size m by n, so that when it's added to A, it basically reproduces A. You can see that multiplication by scalar is distributive. It can be done in any order. And so the C and the K could be reversed, and that would not impact the outcome. If we take a matrix and multiply it by another matrix, that's referred to as matrix multiplication, and that's a little bit different. So we have a matrix A times a matrix B, and A, we'll say, has dimensions m by n, and B has dimensions r by p. So we can only have multiplication if r, the row dimension in B, is equal to n, the column dimension in A. Otherwise, this matrix multiplication cannot be done. So, for example, if we want CJK, and I'll show a picture of this that illustrates it a little bit better. If we want the jkth element of the product matrix, that would be the sum of AJ1, B1K, AJ2, B2K, and so on until you get to the nth element of A. So let me show you a picture of that maybe illustrates it a bit better. In this example, to obtain the element C21, we take A21 times B11, A22 times B21, A23 times B31, and we'll get this element. So it's the sum of all of the products of the specific row and column. So the row in the result corresponds to the row in the A matrix. The column in the result corresponds to the column in the B matrix. So obviously A times B is not equal to B times A in matrix multiplication, because you can see if we were to switch the B matrix and the A matrix and do this in a different order, we would actually run out of columns in B before we finished our multiplication. So that would be an undefined result. Here's an example with numbers. So you can run through the numbers and make sure you follow how this example was obtained. This is for A times B. Once again, if we were to try to reverse this to get B times A, that would not be defined. And so as a general rule, A times B is not equal to B times A. And here's an example of the multiplication of two square matrices. So because they're square, we could certainly reverse the order of multiplication. If we do in this order first, we get 0, 0, 0, 0. If we reverse the order of multiplication and do it in this order, then we get this matrix here. And clearly these two are not the same matrix. And so also noting that when we take A times B, we get the 0 matrix. B times A, we do not get the 0 matrix. So you can't assume that the multiplication is commutative. This is kind of significant because oftentimes in computational approaches to things, you'll be multiplying matrices together in MATLAB. And one way to give MATLAB fits is to try and give it matrices of different sizes that aren't compatible and multiply those two together. So that's definitely something you need to be aware of when using some software tools. Now these are just some matrix multiplication rules. So this one is sort of obvious. If I have multiplication by a constant, this basically just says it doesn't matter what order you do the constant multiplication. So as long as you have A times B, You can either multiply a by the constant and then do the multiplication, or you can multiply a and b and then multiply that by the constant, or you can multiply b by the constant. The order in which you do that doesn't matter. If you have a times b times c, whether you do bc first or ab first also doesn't matter. But what you can't do is you can't do c times b times a, because then that would violate the rule. Also, matrix multiplication is distributive, so if you have the matrix A plus B times the matrix C, you can either do the multiplication of each term first and then the addition, or you can do the addition first and then the multiplication. And this is basically the same thing. So most of the rules with multiplication follow the algebraic rules. The only one is not being able to reverse the order of multiplication. Another definition that's significant is the transpose of a matrix. Basically, you obtain the transpose of a matrix by writing its rows as its columns. So basically, you're just replacing columns with rows. Same is true with the transpose of vectors. So for example, a row vector will become a column vector and vice versa. This is really widely used in a lot of data analysis because oftentimes your data will come in as a column vector, and actually to use something like a MATLAB-based approach and do multiple calculations on your data, you often need it as a row vector. So a lot of times you do need to transpose the data set. For square matrices, you can find the transpose by reflecting the elements along the main diagonal. So you would just flip the upper triangle and lower triangle matrix. So A12 becomes A21, A31 becomes A13, and so on. Some interesting rules: that the transpose of the transpose obviously gives you the matrix back. The transpose of A plus B is the transpose of A plus the transpose of B. Multiplication by a scalar does not affect the transpose operation. And this one's a little bit different. The product AB, take the transpose, is B transpose, A transpose, and this one will show up in some theorems that we'll cover later in the semester. Note that in this particular rule, 10D, the transpose matrices appear in reverse order. So here we have A times B, take the transpose. Here we have B first, take the transpose, and then A, take the transpose. Some more definitions. A symmetric matrix is a square matrix whose transpose equals the matrix itself. And we say a matrix is skew symmetric if its transpose equals minus the matrix. So this is the test for a symmetric and skew symmetric matrix. Here are two examples. The top example, A, is a symmetric matrix. Notice the off-diagonal elements are equal. B is a skew symmetric matrix. Notice the off-diagonal elements are the opposite of each other in sign. A triangular matrix is a square matrix that has non-zero entries on and above the main diagonal or on and below the main diagonal. So we can have an upper triangular matrix where the entries appear above the main diagonal and anything below the main diagonal has to be zero. Or we can have a lower triangular matrix where we have elements that appear below the main diagonal and anything above the main diagonal has to be zero. So any entry that's on the main diagonal can be zero or not be zero. That does not affect the definition. A diagonal matrix is a square matrix that has only non-zero entries on the main diagonal. So any entry above or below has to be zero. So if all the diagonal entries of a diagonal matrix are equal, and let's say they're all equal to the same constant C, then we call that matrix a scalar matrix, because multiplication of any square matrix of the same size by that scalar matrix is essentially the same as multiplying that matrix by a constant. So once again, here we have AS, and if S has only diagonal elements and they're all equal to C, then the basic effect of that is multiplication of that A matrix by the constant C. Sometimes this is useful because sometimes you will actually want everything to be in matrix form. So instead of using a constant, you actually take that constant and you place it as the diagonals in a matrix element. Once again, sometimes useful using some kinds of software. In particular, a scalar matrix whose entries on the main diagonal are 1 is referred to as the unit matrix or the identity matrix. Identity is the term that I use more often. It's denoted by I subscript n or simply I. And basically what the identity matrix does is under multiplication, it gives you the original matrix back. So A times I is I times A is A. And we're assuming there, of course, that we have square matrices. And so if we would have square matrices, then we'd have square matrices of the same dimension so that the multiplication is doable. Okay, so that was a very quick summary of some of the important definitions concerning matrices that we'll look at in linear algebra. And the next lectures will concern applications of matrices.